Okay, so who are we? My name is Aaron Muir. I'm a researcher at the University of California of South Carolina, and I'm also a lead developer of SymPy. Jason Moore in the red shirt back there is a faculty mechanical and aerospace engineer at University of California, Davis, and he's also a SymPy developer and also a developer of a library called PyDyn. Björn Thalgren here in the green shirt is a PhD student at KTH Royal Institute of Technology in Sweden, and also a SymPy contributor. And finally, Kenny Lyons, I don't know where I guess he's over back here in the red, PhD student at University of California, Davis. So this tutorial, we're going to be learning about code generation with SymPy. Some basic SymPy knowledge is going to be assumed, although we are going to do a refresher. SymPy, if you don't know, it's a library for symbolic mathematics. So we just did a big release a couple days ago. If you did the installation correctly and your test script passes, that means you have it. So just a quick, what do we mean by code generation for this tutorial, or just code gen? And for our purposes, this means taking a SymPy expression and converting it to some other language, into code for some other language. So for example, here's a SymPy expression representing some mathematical formula, absolute value, sine of pi x, and this is the equivalent C code. And so code generation, basically you start with the left side and you want to get the right side here. You want to do that automatically. So SymPy supports quite a few languages. If you're targeting or want to target any of these languages, we have support C, C++, Fortran, MATLAB Octave, Python via NumPy, SciPy, Julia, Mathematica, JavaScript, LLVM, Rust, Theano, TensorFlow, and it's very easy to write extensions to these, or to basically to extend to whatever language you want. So this is sort of how I think of code generation, the workflow. Basically, you've got 3 steps, and the first step is you're using SymPy to sort of help you model your problem mathematically using the symbolic capabilities. So you're basically using it to derive formulas that represent whatever it is you're trying to do. And then the code generation step is you want to take those formulas and convert them to something that can be numerically evaluated. And then at that point, you use the thing that you code generation to actually solve your problem. And so code generation is this translation step from sort of the modeling stage to the actual solving of the problem. And then at the other layer here, there's several different abstraction levels for SymPy code generation, depending on how much you want SymPy to do for you and how much you want to do yourself. And this is actually upside down. So at the bottom here, basically SymPy is going to create a Python callable. So if everything's in Python, you just take your SymPy expression, pass it to one of these functions. I think autorep should be in here too, which is what we're going to be showing you today. And it's going to do some magic, and then it's going to spit out a function, and that function is going to be a fast numeric version of your expression. On top of abstraction layer below that is you actually want to generate some code, a larger block of code, but maybe generate the whole function in some language, say in C. And this is going to be like the code gen module. And then the most basic level abstraction is you're just generating the expression, and then this expression is going to go somewhere else in some other code that you've already written. So here are a few reasons why code generation is something that you might want to consider doing. First off, SymPy is a symbolic library. It's a very powerful library. It can deal with expressions in a very high-level way. It can do things symbolically, like take derivatives, or it can solve equations, or take integrals. It can do all sorts of things. You can, by doing things automatically, you can avoid mistakes. So if doing things naively, if you're just writing out your C code by hand, you're going to end up making a typo, a sign error somewhere. by doing things in this higher level way, you can avoid that because SymPy is basically deriving the formulas for me. You can deal with insanely large expressions. I don't know if we're going to show that today, but you can have expressions that are literally millions of lines of code. Would be literally impossible to do by hand because it's very large. But computers are very good with doing bookkeeping, and and then the final is which I also don't know if we're going to be talking about today, but just something to sort of think about is SymPy is a very smart library. It can do it can sort of simplify expressions in ways that standard C compilers or Fortran compilers don't know how to do. It can do things like trigonometric simplification. It knows how to factor polynomials, things like this. So here's a quick outline for today. We're going to try to get through as much as we can. We're going to start with just a refresher for SymPy. We're going to go over some code printers. We're going to look at the easy way to do cogeneration, which is sort of this higher level abstraction I was talking about. Then we're going to go sort of lower abstractions and the harder way, basically. And then we're going to look at doing some Pythonization. And we have bonus material if there's time. But don't be afraid to slow us down. Raise your hand. Jason, do you want to go over the sticky notes maybe at this point?
So we just passed each of you a blue and a red sticky note. We're going to use those during the exercises. You may be familiar with this from software carpentry or other workshops. When we ask you to do an exercise, when you're done, you'll place a blue sticky note on your laptop so we'll know how many people are done. And then if you need help at any time, just put a red sticky note. And one of the helpers, everybody raise their hand that's going to help today. The four presenters, we have Mark in the yellow shirt and Alan, I think. Are you going to help too? And Alan in the corner. So all of us will be here to give everybody a hand. Sartaj too, he's a SymPy dev. So we'll put those red sticky notes up and we'll come around and help you out.
All right, so let's jump in and find, is this the live version? Okay, so let's start with this intro to SymPy expressions notebook here. And so this is going to be a refresher. If you need me to slow down, just tell me to slow down. So quick introduction to SymPy. First step, if you're using SymPy in the notebook, you generally want to use this init printing function. That's going to make it so that things print as LaTeX instead of as strings. It's going to be much easier to sort of see what's going on with SymPy expressions. So the most basic SymPy object are symbols. You create them with the symbols function and you assign them to Python variables. So here I'm creating symbols X, Y, and Z. Also, is the font size okay? Do we need to go up, down? I doubt we need to go down, but is that hopefully better? Okay, good. Okay, so this here I've created three symbols X, Y, and Z, and so yeah, so now I can use these to create expressions, for example, and if symbols is actually pretty smart as far as the LaTeX printing goes. So for example, here I've created a symbols alpha1, omega _2, and it recognizes that these are Greek letters. It recognizes that these numbers are subscripts on the symbols. And so here's say an example expression with SymPy. They just build it up naturally. And so your first exercise now is here's a moderately complicated, hopefully not too complicated expression. You may recognize this function. If you don't recognize it, it comes from the normal distribution. And so your exercise is simply to just create this expression in SymPy. Oh, and I don't have it here, but the square root function is sqrt. So and go ahead and use the sticky notes when you're ready. All right, well, so I guess I'm just going to go over it now. So the first thing is we already defined x, y, z up here. So we have x already defined, but there's two other symbols in here that we don't have defined, this sigma and this mu. Pi is not going to be a symbol here because pi is a number. So pi is already defined by SymPy as this number, but we don't have sigma. We don't have sigma defined yet. So sigma and mu are symbols. And then I'm just going to basically just type it out as I see it. So 1 over the square root of 2 times pi times sigma squared times, and then exponential is just e to exp to the negative x minus mu squared over, and then I need parentheses here to group this denominator, 2 times sigma squared. And you see SymPy has done some automatic simplification, but it's the same expression if you look closely. So are there any questions on this? Yes?
Simplifies sigma squared. It didn't take out of the x squared.
Yeah, so the question is, it didn't simplify this sigma squared, and the reason for that is that the square root of x squared is not equal to x in general. This is only true if x is a positive number. And so we didn't tell SymPy anything here about sigma. So as far as SymPy knows, sigma is just some complex number. And it's only going to do these simplifications based on what it knows is true for all complex numbers. So if I knew, for instance, that these were positive, I can type positive equals true here in the symbols function. These are called assumptions. I don't think we're going to be using assumptions a whole lot today, but this is one way to get SymPy to do some of these simplifications, especially relating to this square root of x squared deal. And if I do that, now you can see it knows the square root of sigma squared is just sigma. So good question. Thank you for bringing that up. All right, so now I want to go over just some important things that can trip you up using SymPy. These trip up everybody. So I think that one of them already tripped somebody up. At least one person up in here, probably a few of you. So if when SymPy evaluates an expression, basically Python just evaluates it, and SymPy has operator overloading. But when Python sees sort of this integer divided by integer here, this 1 over 2 here gets evaluated before SymPy ever gets kicked in. And what Python's going to do to this is going to create a floating point number. So you can see here we have x plus 0.5, which is sometimes that's fine for what you want, but often SymPy works better if you use exact rational numbers instead of floating point numbers. And so the trick here is you just use the, you can use either one of these forms. You can use x plus this little s function. Basically, this is gonna convert this 1 into a SymPy number, and then it knows that SymPy number divided by 2 gives a rational, or I can do x plus the rational number 1/2. And so now we get an exact number. And this is only an issue if you're dividing basically integer literals, because Python evaluation order basically kicks in. So if you have an issue where you're getting floats where you don't want them, you can just wrap your integers with this s function. Second gotcha, which hopefully you knew this before this previous exercise, but in Python the caret is not the power operator, and SymPy follows Python conventions. So caret is actually XOR. This is a logic expression right here, which is not what you want. So you have to use this double star. And then the final gotcha, all SymPy expressions are immutable. So if you just remember that. So no function anywhere in SymPy is going to change a SymPy expression in place. It's going to always return a new expression. So right here, I've taken this thing x plus 1, I've assigned it to the variable expert, and now I'm using this function subs to evaluate that at x equals 2, and so that gives me 3. But this does not change the original expression expert. I still have x plus 2 on here. So this subs is returned a new thing here. Okay, are there any questions on what we've done so far? All right. So the next thing is floating point numbers. SymPy, in addition to doing symbolics, has the ability to evaluate numeric expressions, exact numeric symbolic expressions, and it's a floating point number. So here's the exact expression for square root of 2, and if I use the evalf function, that's going to give me a float. And here, if I just do evalf, I get a float. If you put a number here, like 7, that's going to give me a floating point number with 7 digits. So, and SymPy has arbitrary precision, so I can put any number here I want. I can put 100, get 100 digits of this. So now your exercise is to compute 100 digits of pi. Okay, see a lot of blue sticky notes. Not intended to be a difficult exercise by any means. So yeah, we just take pi and call the evalf method on it with 100 as its argument. And here are the first 100 digits of pi. And of course, if you want, you can play around with it. You can do 10,000 digits of pi. Eventually, it's going to start taking a little longer to compute all those digits, but there you go. Where do we actually? Oh, okay. So the next thing to go over as a review is the undefined functions. So up here, with the symbols, these create just variables. But if you want to have something that actually depends on another variable, then you need to create a function. And this is important whenever you want something basically to have a derivative that depends on a variable is typically where this ends up getting used, at least in terms of cogeneration. And so there's this function, you call function and then the name of the function. And so that creates a function called f. This is an undefined function, and so now I can create expressions with f of x. And so now this gets used by the, we'll see here, it gets used by the derivative functionality. So to take symbolic derivatives, we use the diff function. And then the syntax is you just do diff and then the variables that you want to differentiate. So here we have this expression, sine x plus 1 times cosine y. We're going to take the derivative with respect to x and then the derivative with respect to y. And so, you know, if I do this stepwise, here's the derivative with respect to x. Here's the derivative of this now with respect to y. And this also works with undefined functions. So if you want to build an ODE, this is how you build an ODE. Basically, you take the derivative of an undefined function, which is going to be our next step, actually. So your exercise now is to basically write an equation for this wave equation. And remember here, this is sort of implicit in the way this is written, but this u here is not going to be a symbol because u depends on two variables. It depends on t and x. And then one final thing is if you want to write something with an equal sign here, you can use this eq function. So go ahead and do this exercise. All right, well, so I'm going to go over it. So the first thing is we need to define this u function. So u is just function u. And then u is going to be a function of two variables. And I'm sort of free how to write that, but I'm just going to write it like this. Oh, and we can see already that t is not defined. We never defined t. So, and we also notice up here that we didn't define c either. So I'm going to just define those. T and c are t and c. And so now I have a function of t and x. And so I'm going to use this EQ object. And so the left-hand side is the derivative of this with respect to t twice. And the right-hand side is c squared times the derivative of u tx with respect to x twice. And just to show you something here, you can either write t comma t, or you can just write the number after the variable for the number of times to take the derivative. Any questions? I'm going to leave that up there for just a little bit.
Question.
Oh, you have a
Could
question?
done this, u could have been a function of t on the left and a function of x on the right.
That's right.
It still would have worked, but I'm assuming that would mess us up later.
Well, yeah, so I mean, I can also, I mean, you gotta be consistent. SymPy, this undefined function SymPy doesn't know anything about it at this point. Doesn't know how many variables it has, doesn't know, what variables it's supposed to be with respect to. So yeah, I could have also written this whole thing as x comma t, if that makes more sense to you.
No, I was thinking even worse, like only a function of x on the left, or only a function of t on the left. And only
Oh, okay, well, yeah, so that would be wrong. That would actually, that's not what this equation means. And you can see here, so let me actually show this. So if you notice the difference here, SymPy is even printing these differently. This one it's printing to D, this one's printing a partial. So this one here is a partial differential equation. This one is some weird ODE where we've used a different variable on the left-hand side than the right-hand side. But this is not the same thing as this. So this is what you get on Wikipedia, and they tend to leave out the of t and comma x everywhere because it gets tedious when you're writing it down. But SymPy needs to know what variables it depends on. And yeah, we can write things that don't really make sense physically, but they make sense mathematically. I can write, I can pretend like it's just one variable here. I can get my variables backwards. So you need to keep things straight. One thing that helps if you're writing differential equations, let me actually cut this. Let me delete this cell. So one thing you can do, instead of defining function u equals function u, I can just write this. So that way the variable u is always just going to be this function at tx. And so if I'm never going to use u for anything other than calling it at tx, then I can keep this like this.
That seems like a really good idea.
It's a good idea if you never use it except in this context, yeah. The thing where this can trip you up now is if you try to call u, if you try to evaluate this isn't the function, this is the function evaluated. So you'd have to do, you'd have to do subs, say at t0 x1. But yeah, if you are creating differential equations, this can save typing and mistakes and stuff. Any other questions? All right. Matrices, this uppercase M matrix function creates matrices. There are several different ways to create a matrix. If you look at the help, you can see them, but the most simple one is just a list of lists, and you can see here that these are basically the rows of the matrix. So 1, 2, 3, 4 here. And if I pass just a list with one level of nesting, this is going to create a column vector. And so matrices in SymPy can contain anything. They can be symbolic expressions inside of them. So here's a matrix with x, y, z. And matrices, of course, they support all the matrix operations that you'd expect. So I can do times here. I think we're actually running Python 3.5 here, so I can use this matrix multiplication operator too if I want. But SymPy does just use the times symbol on matrices for multiplication. And there's a whole bunch of other advanced things you can do. For example, I can take Jacobians. So here's the Jacobian of this matrix with respect to x, y, and z. And so now your exercise is just create, your exercise is actually 3 parts. So first create this matrix, and you're probably going to want to save it to a variable because you're going to use it for the next part. And then second, create this matrix and multiply it with this one, and that should give you this matrix. And then finally take the Jacobian of your of this matrix.
Take your blue notes down until you got it done. Red.
And I'm just gonna leave this up so that you can see this part. All right. Well, I see a lot of blue stickies, so I'm gonna jump ahead here, try to type out this answer as fast as I can. So 1, 0, 1. Negative 1, 2, 3, 1, 2, 3. Oh, and I'm just going to call this M. And then my vector is going to be x, y, z. And since it's a column vector, I just write a list here. And then, so now I want to do M times V. And let's call that A. And so now I want to take the Jacobian with respect to this. So I can just do Jacobian V here. Or I could retype out X, Y, Z. And you may notice this is going to be familiar. This is the same thing as M. So if you take a constant matrix times a matrix of variables, and then you take the Jacobian, which is basically the matrix derivative. The derivative of constant times a variable is just the constant again. Okay, so one more thing in this notebook. Question? Oh, sorry. Yes.
Just a quick question. So you have the vertical X, Y, and Z matrix.
That's right.
What if you wanted like the horizontal X, Y, and Z stuff?
Okay, so if you want a row matrix here, so I can type this as a nested list X, Y, Z, just using the same syntax here. So if I have nested lists, then each list here is a row. I can also type v.t. That'll give me the transpose of this column. Either one of those will give you what you want. All right, so final thing is these matrix symbols. These are useful in code generation for representing matrices in the code that you're generating. And so now I'm creating some integer symbols and have a matrix symbol M, matrix symbol B. And this here, this second and third argument is going to be the shape of these matrices. So I have M and B here. I can take M times B. And so I see here, for example, M dot shape. This is an N by M. M is an N by M matrix, and B is a M by 1 column vector. And so I can multiply these. Their shapes align. And yeah, if I take the shape of the product, it knows that the shape is N by 1. And there's different functions you can use on matrix expressions. The transpose, for example, A lot of functions don't actually evaluate unless you call this do-it method. So you can choose whether to have it transpose evaluated or not. And what do you think? Do we have time for this exercise or should we skip it? Well, I have 20 minutes for my next notebook, so if you want to do this exercise, by all means, do it, but I'm going to skip it. So, and there is also some material down here if you want to learn some more. I think our latest version of our tutorial is not actually going to use anything below this matrix expression, so it's not something that we need to know. All right, so now we're going to the code printers. And this is just going to be basically kind of showing off more than anything. We're just going to show you all of these languages that we support in SymPy. So here's a function. I chose this function because it sort of has a good demonstration of how different languages represent things mathematically. So absolute value sine of x squared here. And we can see how is this function represented by different languages. And so we can just run through here. All these functions are going to take an expression and convert them to a language. Okay. Yeah, so the first one is C code. That converts it to C. So we can see absolute value is now fabs. Power is this power function, which will, F code is Fortran, which looks remarkably like Python, which is not a coincidence. In fact, it looks exactly like the Python code. Here we have Julia. Julia looks pretty similar too, except they have this this different power operator. JavaScript. Everything is prefixed with the math. Mathematica. The MATLAB printer is called Octave code, but the code generated by Octave code should work with Octave or MATLAB. This Rust code is new in the latest version of SymPy. So this is what this function looks like in Rust. Here we have R, and here we have C++. And I forget what the default standard is for C++. Yes, Nathan?
So a lot of those aren't valid unless you include libraries or actually other code besides those. Is there something in SymPy that says
So
generate like the error block or whatever for
So I think like, for example, the C one is just going to assume you have math.h, for example. We are going to go over later, yeah, like you know, so this is sort of going back to here. This is sort of this top level of abstraction. We're just generating an expression. So later we're going to look at, okay, what happens if we want not just the expression, but we want some other code that goes with it, like a header and some stuff to wrap around it. And also, if you look, all of these functions have options to them. So C code, for example. So C code, I can change the C standard that I'm targeting. I can decide to assign it to a variable, whether it's going to be dereferenced, things like this. And so, for example, F code. Let's look at F code. And I don't think this is actually, yeah, so these are the different Fortran standards. I think this expression is the same regardless of what standard we use. Yeah, so the default standard is it 95? No, it's 77. Yeah, so, oops. So that's the default standard. This expression doesn't matter, but other things might. So yeah, your exercise is just play around with this. Come up with some functions, see what works, see what doesn't work, what's different for different languages. A lot of these printers, some of them support more things in SymPy than others. So you may run into errors. And, if you have any questions or observations, feel free to raise your hand or use the red sticky note. So how are people doing? Anybody discover anything interesting? Which of these languages is the most different from the others? I personally think that Rust is the most unique language here, at least in terms of its syntax.
Anything print unexpectedly? What you would expect for that particular one?
Does anyone here consider themselves an expert in any of these languages? Are we only Python experts here?
Do any of the languages support derivatives?
So the question was, do any of the languages support derivatives? So do you mean like taking a numeric derivative or?
Well, I just made a derivative expression.
Oh, yeah. Well, so probably not. That's something that you would get out of like a numeric library. So, like for example, a NumPy would have a derivative function. Yeah, but derivative would be more like a subroutine call. For the most part, if you have an expression and in SymPy, you just take a symbolic derivative and then generate that. Okay, we'll start with you here.
So I'm getting hyperbolic tangent not supported in JavaScript. So
Is it true?
when it tells you something like that, is it usually like abandon hope, all you who enter here, or?
Well, I don't know JavaScript very well. Does JavaScript support hyperbolic tangent in the math library? If you have a JavaScript library that supports it, you can extend the printer. I don't know if that's something we're going to go over later about how to do that. Or if hyperbolic tangent, oh my gosh. So that's tan h of x. So we can use SymPy to rewrite this using exponentials. And it does know how to do this. So yeah, this another powerful thing about SymPy is it knows these identities. We had a question over here.
Yes. What is it like before translation has like empty spaces at the beginning? Is it
Okay.
like-
So the question is, why does Fortran put some spaces? And that's a good question. It's because this Fortran printer is kind of
You can enter format equals 3 as a keyword argument, and you get
like that.
yeah.
Mm.
I think you change the standard.
Oh, no, it doesn't. It doesn't know what format means. It's because it's one of these things that we might actually end up changing. It's because it's sort of designed for inserting into a function.
19.
Oh, just the 90 standard doesn't do that? No. There's a way to do it. Yeah. So this guy is standing in the back. Björn Dahlgren is actually a Google Summer of Code student this year, and he's working on improving our cogeneration. So we have a lot of sort of dusty corners like this that might end up being cleaned up.
Is there a reason why the Rust and C++ printers aren't in the main SymPy namespace yet? Or was that just over?
Well, they're brand new. The question is, why are Rust and C++ not in the main namespace? Honestly, they probably could be, especially C++. I don't know what you guys think about that. I mean, given that the rest of these are, I think I don't think there's any reason that they shouldn't be. It was probably just an oversight when they were added. It's always easier to add something to a namespace than to remove it. Are there any other questions? Otherwise, I want to move on to this last exercise for the last few minutes of my section. And this is sort of going more in depth on this JavaScript printer. This is just some boilerplate you should execute. And that doesn't work. Interesting. Why don't I have the library installed? Oh, I know why. Okay, so I'm actually a very bad person. I didn't actually activate the environment. But all you guys did, so it's going to work.
You were just showing us, right, what would happen if you did it.
That's right. Okay. So let's make sure this stuff's imported again. Okay. So if you run this boilerplate, we've got a little some JavaScript template here. It's not too important what this is doing, but we're basically using a library called chart.js, which is, some fancy JavaScript thing. And we've got a lot of boilerplate here, but if you look at this fill me in, basically we're saying here's two functions, f of x and g of x, in JavaScript, and these are going to end up getting plotted with this library. So let's create two functions. Here's sine. So let's say the first one is sine x, the second one is cosine x. And there's also this chart ID, which is, again, JavaScript stuff. You can just put anything in there. And so I want to convert these to JavaScript code. So for example, JS code F1 is going to convert sine of x to JavaScript. And then so I plug that into this JavaScript template. And so our top function now is going to be sine of x, and our bottom function is cosine of x. And so, maybe I can try different things here. So here's cosine of x squared, for example. And so your exercise now is here's two equations. They're intentionally quite complicated equations, but your exercise is now to just plot these as your top and bottom. Yes?
So when I print the code for a matrix vector multiply, I just get A star B. Is there a reason that doesn't expand out?
So the question is, you print a code for a matrix vector in JavaScript, you mean?
In C, for example.
Oh, in C. So the question is, why does the matrix vector multiply not expand out? So it doesn't, we're basically assuming that if you're multiplying two vectors, you're going to be using some library to do that. So it's not really supported directly. The thing that we'll be using matrix symbols for is sort of accessing the different elements of the matrix. So doing something more complicated than multiplication. But yeah, so that's something, if you wanted to support just multiplication, you would need to tell the printer, what you're assumedly using some matrix library to multiply for you, so you need to tell it what that function is. And so let me go back here and just show you. And we'll get to this later, but if you look at, I wonder if this saved at all. Yeah, so if you look at this, A here, let's wait for MathJax. Here we go. Oh, that's not the one I want. That's not even the one I want. This one. All right, so if you look at this m times b, this thing here is this matmul object. So what you would be doing is telling the printer how to print matmul objects, and you tell it whatever C function, and that's what we're going to go over later. Are there any other questions? I see a lot of blue stickies, so I think I'm just going to go over this. We basically just copy paste here. And so this is going to be our top function, the bottom function. And so these crazy equations end up plotting something looks like this. These are the Batman equations. All right, so are there any other questions on the last two notebooks that I went over? Yes? There is a Python code printer, but it's something that needs to be cleaned up, actually, so we didn't include it in the tutorial. Right now there isn't actually a very clear just Python versus SymPy code printer. That's something that we were going to try to clean up, but I guess we didn't get to it. But yes, you can definitely cogenerate to Python itself or to Python with NumPy or Python with SciPy. Do you have a question?
Yeah. So on the plotting along the x-axis, all of the labels are these really long decimal numbers for the sine and cosine functions. It'd be really great if they could be in terms of pi. Is there any way to make the labels in terms of pi instead of those really long?
Well, it's whatever's going on in this charting library. I didn't write this JavaScript template, so
you just have to read.
you would need to tell chart.js how to get the labels. Yeah, the question was about these making these labels look like something nicer than just long floating point numbers. All right. Well, if there's no more questions, that's the conclusion of my section. Who's next? Björn? So the question now that we'll have to decide on is, are we going to, do we feel like we need a break now, or should we break after Björn's section in an hour?
Raise your hand if you'd like to break now. Order of people. Let's take a few minutes.
All right, so yeah, quick 5-minute break, and then Björn.
As Aaron said, I'm actually working this summer on a scholarship from Google, on Google Summer of Code, to work on the cogeneration capabilities of SymPy. So we had a question about the Python printer. So there is a Python printer, but it prints code that assumes that we already have SymPy in the namespace. So that's quite suboptimal. We're working on changing that. So my name is Björn, and I'm a PhD student in chemistry, or computational chemistry, in Stockholm, Sweden. And my part here will actually be looking at the easy way. So we're going to try to use functions that generate Python functions. And we're going to apply it to a few examples. So a raise of hands, how many people here are familiar and feel comfortable working with ordinary differential equations? All right. So that's the vast majority. So we're going to skip the notebook on ordinary differential equations. And those of you who need a refresher, you can have a look at that notebook. So we're going to skip ahead then, straight to the notebook called Lambify. So Aaron showed us some examples where we could evaluate the expressions numerically, and he did so using the eval_f method. So if we import SymPy into our namespace and just take an arbitrary function, depending on two variables, so mapping R2 to R1, we can run the subs command and exchange our variables.
Bump up the font size.
Oh yeah, sure. Is this better? All right. So running the subs command and eval f gives us a numeric value for this expression. The problem with doing this is that it is quite slow. This eval f is a general arbitrary precision function. So if we would time this one, we see that it takes almost a millisecond for each call. And if we compare that to a pure Python function of the same, representing the same equation, we see that it runs in 3 microseconds. So if we're doing this in a tight loop, doing some numerical computations, this becomes problematic. So, and we don't want to write this Python function by hand. So there's a function in SymPy called lambdify that generates Python code, executes the eval function on it, and gives us back a working function. So running lambdify gives us g, and if we time the g function, we see that it's just as fast as the Python version. Another good thing about using lambdify is that you can change what backend it targets. So we can have it generate functions using NumPy functions, which then broadcasts to arrays of arbitrary shapes. So if we run lambdify, and as of the latest version of SymPy, which you all have, the default is that it's going to use the NumPy backend when available. We can see that we can give h an array here, and it will give you an answer which has the same shape. So this is the NumPy broadcasting that kicks in. And this is just to show this once more. If we have 2 arrays, 1 or 2 vectors, a column vector and a row vector, and give this function those vectors, it will do the NumPy broadcasting for you. So the out shape is the number of rows in the row vector and the number of columns in the column vector. Sometimes it is important that you have control over the function signature of the function that's generated by lambdify. It can be because of you're using a numeric solver from the SciPy library, and it has certain requirements on the signature. To specify this, we just give an arbitrarily nesting of our arguments in the first argument passed to lambdify. So in this case, we will have a symbol sed, which is actually a tuple of 3 symbols. And it means that the function generated by lambdify here, function 2, will expect to get a length 3 tuple as its third argument. So this works as expected. So now it's time for you to do an exercise. And we have this little exercise line magic in the Python notebooks. So if you run the first few cells, and evaluate the exercise cell once, it will expand, and you need to fill in the triple question marks here. If you want to take a sneak peek on the solution, you can rerun that same expansion, but instead of using that exercise magic, you can use the load magic. So this would give you the solution, but I'm not going to run that one. So yeah, give it a shot and put up the blue sticky notes when you're done. Yeah, so there was a good remark that we got. We can change this matplotlib inline to be matplotlib notebook. And if you change that, you actually get an interactive widget, which allows you to manipulate the data and look at it from different angles. Question?
What does the matplotlib notebook give you as opposed to the matplotlib?
Oh yeah, I think most people are getting done. So let's take a look at the solution. So getting the partial derivative there, the mixed partial derivative, we need to write x and y. And the function which we're interested in is the lambdify function. And running, we can first run this with inline. It will give us a PNG image, which is static. So I can't really rotate the axis, I can't zoom, I can't do anything with it. If I rerun this with the matplotlib notebook magic, might have to rerun it. Huh.
I had to rerun the matplotlib.
Okay, all right. The
19.
Yeah, just run that itself.
Oh yeah, there we go. Thanks. So now you can actually grab this, and supposedly you can actually rotate the graph, and it re-renders as this three-dimensional picture, and you get a sense of the depth. All right, so that was our exercise notebook on the lambdify function. Let's now take a look at the next notebook and see how we can apply this to an example from chemistry. So let's move to the chemical kinetics introduction notebook.
This is something that changed in the last version. Previously, now it's default. Yeah, sorry, so you should be.
All right, so chemical kinetics is actually the study of the time evolutions of concentrations in reactive systems where we have competing chemical reactions occurring. So we will be looking at a rather simple but yet interesting chemical reaction, and it's the formation and breakdown of this molecule nitrosyl bromide. But before we look at that actual case, we need to look at the governing equations. So the most rates of chemical reactions follows the law of mass action. So that the rate of change is proportional to the concentration of the reacting species, raised to the power of their multiplicity, which they are appearing on the reacting side. And then we can formulate ordinary differential equations as a sum of contributions from all the different reactions. And for a constant temperature and pressure, there's a coefficient, which is the rate constant, which, yeah, as you hear, is constant. But it's often under the assumption at least constant temperature. So the law of mass action looks like this. And studying this chemical reaction, we have two processes, a forward process forming nitrosyl bromide, and a backward process where it decomposes into three constituents, 2 NO molecules and 1 Br2. And we were just going to rename these to C1, C2, and C3, the concentrations. So NO, Br2, and NOBr are just 1, 2, and 3. Those are the chemical species. And applying this law of mass action gives us then this system of ordinary differential equations. So it's a three-state problem. You can actually reduce this by applying such mass is preserved, for example, so that gives you a relation so you can reduce the number of states here, but we're not going to look into that. And that above equation had two matrices in it, this S and R matrix, but the details are not that important right now. So we're going to look first, how can we just write this using NumPy, SciPy, not using SymPy, and then we will look at what can actually SymPy do for us, which helps. So doing this numerically, we will be using a numeric solver from the SciPy library called ODE-int. Raise a hand, how many people have used this or another solver for ODEs in SciPy? All right, a few. Okay, so then what it needs is that we need to have the right-hand side of our system of ordinary differential equations. That is these three expressions. So we need to have a function evaluating these three expressions. So in this case, it's just hard-coded. We say that we have two reactions, forward and backward. They have this form from the law of mass action, and we just return a list of size 3, which is the numeric value of the derivative of each concentration with respect to time. And if you look at the function RHS, the right-hand side here, we see that it has this signature that it takes y, which is a state vector, and then a scalar t, and then two scalars. And it can be any number of parameters passed to the solver. The important thing with these trailing arguments is that there are parameters which stay constant during the time of integration. All right, so it's time for an exercise. So you're supposed now to give the arguments to ODE-int. So this has not anything to do with SymPy in particular. It's just reading the documentation string for ODE-int. You can do so, maybe the easiest way to do it is to insert a cell and write ODE-int and then a question mark, and then hit execute, and you get the documentation. All right, I think most people are getting there. So in this case, the arguments are named quite nicely. The first argument is the function, which needs to be called, and that's our right-hand side function. And then it's the initial state vector, what we start with. And then we need to specify the time points for this. Where are we interested in getting this state vector? At what times do we want to know the concentrations? So that would be our T out argument. Then the tricky part might be how to specify these arguments. So in this case, it's just a tuple or our k values. So that k vals. All right, so the integration is done, so we can plot the solution. And yeah, looks good, nothing weird's happening. This one can actually be solved analytically, and SymPy can do it for us, but we're not going to look at that here. And writing this right-hand side function by hand, well, it wasn't that bad for this system, but the number of terms increases rapidly as the number of species and as the number of reactions increase in your system. So you usually want to do that by some system. And if you choose to represent it using SymPy, you get additional benefits, as you will see. So we're going to construct it symbolically, and then we're going to have SymPy generate a function using lambdify, and then we'll look at what more can be done here. So this is also a nice feature of using SymPy in your workflow, that if you generate symbols and symbolic expressions, you know that you can take the LaTeX output from these equations and put it in a paper or a report, and you will know that the equations in the report are exactly those that you used when you ran your simulations, because it's, at least to me, it happens every now and then that you write one thing in the paper and in reality there was a minus sign in the code or something.
By the way, the LaTeX, if you do want LaTeX output from an expression, the function is called LaTeX, and that returns the string.
Yeah, so for example here, we can look at the first element in this vector. We can just run the LaTeX command there. Okay, so it's time for another exercise. Now we're just going to construct a function from this symbolic expression. All right, I think most people are getting there. So what we need to remind ourselves of is that the ODE int function from the SciPy library, it needed a special signature, right? So if we look back at the right-hand side function, we see that we have a state vector and then 3 scalars, where the 2 last scalars are the arguments or the integration parameters, which stay constant during the time of integration. We can construct those by making a tuple called args maybe, and have it be the symbols y, t, and then we add the tuple of the k values, and this will then look like this. Oh yeah, the symbols t needs to be defined. All right, so that gives us the same solution. So this didn't add that much, but for a large class of problems, when dealing with initial value problems with ordinary differential equations, these problems may become stiff. And when they are stiff, you need to use an implicit solver. And the implicit solver would need the Jacobian of the right-hand side. That is, we need to form the matrix where we take the partial derivatives of each of the rate equations with respect to each state. And SymPy can generate this quite easily for us. We just write Jacobian, and it's done. And then we can use this together with lambdify to give us an analytic expression or a function evaluating the analytic Jacobian. And this can be the difference between a successful integration and a failed one. Because what the solver usually does or what it does if it wants to use an implicit solver and it does not have an analytic Jacobian, is that it's going to be using finite differences. And depending on the scaling of the variables of the problem, these finite differences may or may not be accurate enough. So it can really be a dramatic difference to give this function. All right, so then we're going to take a look at the final notebook for this part of the tutorial, the easy part. And it's more of the same. It's still chemical kinetics, and we will be looking at how to construct the expressions symbolically from the start, because this time we had the right-hand side function, and we had already done the work of transforming or rather hard coding the right-hand side of the ordinary differential equations into Python, and we don't want to do that. We want to have some domain-specific representation and just from that construct our equations symbolically. So in this notebook, we will be looking at the Robertsons example. So it's an example from the 60s. It's chemical kinetics, and it's interesting because it's a stiff problem. So it's been a challenge, even though it's just a free state problem. It's just only has 3 variables. It's been a somewhat of a benchmark for numerical ODE solvers. So we have 3 chemical species, A, B, and C, and there are 3 reactions. One is the decay of A into B. One reaction is between B and C, forming A and C. So C acts as what's known as a catalyst. It is not consumed in this reaction. And the final reaction, which is a bimolecular reaction converting 2 B molecules into B and C. And what you can say by just looking at these 3 reactions is that C is never consumed, right? The only time C is on the reacting side is in the second reaction, and there it's reformed. So this system will have a solution at infinite time where your molecules will be converted into C. So again, applying the low mass action, we can write the ordinary differential equations. But this time, we're going to be representing it as a tuple of a coefficient and 2 dictionaries, which specifies the stoichiometric coefficients of each species on the reacting and product side for these 3 reactions. So we will start with an exercise for you to complete the function constructing the symbolic representation of this right-hand side function. So this is the vector which was known as y dot in the previous notebook. And depending on how familiar you are with Python, this may or may not be a hard exercise, so don't feel too bad if you get stuck. All right. Okay, so I'll give you the first part of the solution, the first 3 question marks there. So if you look at the equations below, this corresponds to the product. So we need to raise the concentration of the species to this number R. And the concentration of the species is symbolically available in the C dictionary. And then we need to have the right key, and that's given by the dictionary which we're looping over. So that's RK. And the dictionary values is that stoichiometric coefficient. So what's left now is this part, which corresponds to this summation here. The details here are not that important. I see some more blue sticky notes coming up, so I'm going to give you the final part here. So it's just the net multiplicity multiplied by this variable r, which we computed just before this loop. So the only thing that's important here, that this function, in a general manner, does what we hard-coded in the last notebook, that right-hand side function. So now we can just give it these kinds of dictionaries, and it will do the right thing. If we actually run all the cells. All right, so that looks familiar from the introduction text. So in the next step, we will do the exact same steps as we did in the last notebook. We will create a function, a Python function, evaluating this expression using Lambdify. And you recognize the signature from the last notebook. And we will run the integration with some parameters from the literature. And what's interesting here is that the solver tells us that it has evaluated the Jacobian a number of times. But it's kind of weird because we haven't given it the Jacobian. So it did just what I said for the last notebook. It approximated the elements of the Jacobian matrix by doing finite differences. So we'll see if we can provide this function manually or using SymPy to give it an analytic expression. So the next exercise is for you to do just this, to make a function evaluating the analytic Jacobian. Question?
Scroll up to where you put the solution to the previous exercise.
The
The make expression sims thing.
You can also use percent load to get the solution.
Yeah, I can show you how to get the solution. So if you just delete the contents of this cell and uncomment that magic command, change exercise to load, and evaluate the cell, you get the solution here. So it just says exercise in the comment. All right, I think most people are getting there. So what we were looking for here was, as you saw in Aaron's introductory notebook, you can run the Jacobian method on a matrix to get its Jacobian. And if you look at the documentation of the ODE int function, you see that this defun argument, it requires the exact same signature as the func argument. So again, it's just the y comma t plus k signature again. And running the integration with this function given as defun, we see that it did not need to evaluate the Jacobian quite as many times as when it was not available. The difference here is quite small, but it's mainly because this is a very small problem. It's only three variables. And on this, you can, even on this small problem, you can actually see a small impact on the total running time of the integration. It's slightly faster giving the analytic Jacobian. But as the problem grows bigger, this effect grows quite rapidly. So are there any questions at this point? All right, so we would appreciate if you just write some feedback on the sticky notes and some negative feedback on the red one and some positive on the blue one. Was that it? Yeah. All right. And then we'll, yeah, take a 5-minute or 10-minute break. Okay. So, yeah. 10-minute break. So we'll be back here 5 past.
Okay, I think it's 5 after according to my clock, so we could go ahead and get started. So I'm Jason, as Aaron mentioned before, and we're going to move into the third section, the third hour. The title is The Harder Way, C Code Generation, Custom Printers, and CSE, which stands for Common Sub-Expression Elimination. So Björn just showed you a high-level look, use of the code generation facilities in SymPy. And now we're going to start to dig into that and sort of expose how some of that works under the hood, how you can manipulate and change how it behaves, and that'll lead into the final lesson 2 that Kenny will deliver. That'll show you how to further make use of these things. So if you open up the Harder Way C Code Generation notebook, you can read through some of this intro here, but the main learning objectives that we're going to tackle during this next hour, we're going to use a code printer class to convert a SymPy expression into compilable C code. So we're going to start looking specifically. Font size up? Oh, every notebook you got to do it. Is that good? Thank you. The first one is, okay, we're going to generate C code, and we're going to generate more complex C code. Secondly, we're going to be working with arrays in C, so we're going to transform various SymPy expressions into array-compatible code. We're going to learn how to subclass the different printers in SymPy to have them behave differently. We've had a few questions already about, well, what if you wanted to print something differently than what the defaults are? So we'll show you how to change that. And then finally, we're going to introduce common sub-expression elimination, which is a pre-optimization that you can potentially use to speed up your computations. So those are the main things. We'll go ahead and import SymPy and turn on the pretty printing. And which notebook? This is, how do I get back to that? Yes, 7, the hard way. And you can link to it from the index right here. And the title is 707, the hard way. Got it? Anybody else? Okay, so I've initialized some things. Björn just introduced you all to these chemical kinetic problems, and he gave a couple of textbook examples. He works on bigger problems, harder things to solve, more complex sets of chemical reactions. And in particular, he is going to, I'm going to use one of his sort of research level sets of ordinary differential equations that models how water is exposed to ionizing radiation. And you might find this in research about nuclear reactors and such. I don't know a bunch of details about that, so I'm going to not talk that, but if you want to ask, we'll get Björn to answer more detailed questions. But the gist of it is that we still have a set of ordinary differential equations. In our case now, we're going to have 14 states. And I'm already screwing things up. Okay, back here. We have a function that just loads in these symbolic right-hand side of the ordinary differential equations, the f of yt, and then the value states, which is y of t. So as a first exercise, have a look at these, investigate maybe what types they are, what the expressions look like, how complex are the mathematics. Spend a couple of minutes doing that. And you can put up your blue sticky notes when you're done, and your red if you need help. And one other note, so I have a little bit different solution. If you want to see the solution, you can double click this cell and it'll reveal an answer. May not be the only answer, but an answer to that. But go ahead and give it a try first. Okay, what did you all learn? What do we see? Anybody like to volunteer? What kind of equations do we have? Polynomials. So if I, nonlinear polynomials. So if I just print this to the screen, it'll actually render, and I have a vector of expressions that are multivariate polynomials in these 14 different state variables. So these equations look a little nastier than before, being that it's more of a non-toy problem. But this is also stored in a matrix, and then you can check the type to, or I'm sorry, the shape, 14 by 1, and then our state vector is also a 14 by 1 of the various symbols in there. Okay, so you've learned about the Jacobian now in the 2 previous notebooks, so go ahead and compute the Jacobian of this function of the states, and then take a look at that too and see what you get, and if it's what's expected. And you could take down your blue sticky notes and then put them back up when you got it. So it looks like about half of the people got something. Put your blue note up if you've got it. So what do people find here? So you can use the Jacobian method as we have before. What do we end up with? You already answered.
An awful matrix.
An awful matrix. That's what I like to hear. So we've got now a large matrix, and if I look at the shape, which Sartaj informed us of, 14 by 14, and I'm seeing one column right now, and I have a bunch of linear expressions in the states, and you can do this on your own screen too, scroll through and just sort of see. We got a bunch going on there. 196 entries, handful of them are 0, it seems, but most of them have some small expressions in the linear expressions in the states. So I think, hopefully these 2 examples here give you some idea that when you have a non-toy problem, this is a little unwieldy to handle by hand and try to type yourself. So this is particularly very useful, and we can work with these and start to generate code from them, and then be able to evaluate them numerically. So let's talk a little bit about C code now. So we're going to start printing C code, and I think we had some questions earlier. Well, how do I include libraries? How do I have more than just printing a single line of code? And we're going to sort of give some idea now of how you might make a compilable piece of C code that was generated by the expressions that we just saw. So here I have a template for a C program. We include both the math library, which we're going to use a lot of the math functions, and the C code printer automatically assumes that we'll be using those. And I've also included the standard input-output library here too, so that we can print out some results to the screen. If you recall, how many people are comfortable writing C programs? Raise your hand. Okay, good. So at least half, maybe a little more. I'll give a little refresher here. And in general, we need there's always has to be a main function, and the function looks like this. There's a return type on the left, and then within the curly braces is what that function does. So our main function, when we run this program after it's compiled, it will execute the lines in this function. The first thing that I do is I introduce some variables, okay? And we're going to work with arrays sort of explicitly, and I'm going to avoid talking about pointers and things, but just sort of talk about this in the context of an array variable. Everything in C has a type, right? So these are double precision arrays. This is the name of the variable, and then this value here tells me that it is 14 entries long, 14 double precision values. And then I assign some default values to the states, right? Just some example numbers here, 1 through 14. With that command, everything has to end with a semicolon. And then here, I also have to introduce 2 arrays to hold the results of our computations. And these are essentially empty of sorts when I create them if I don't initialize them. But when I evaluate the right-hand side function, that's a 14 by 1, so we want 14 entries. And then we're also going to map the 14 by 14 Jacobian to a 1D array where all the rows are stacked of 196 entries. Okay, so we're going to just use 2 simple 1D arrays to store the results of that. We're then going to call a function that we're going to create, and that's evaluating the ordinary differential equations. It's going to take whatever the state values are, which we predefined, and then it's going to pass into these 2 empty arrays that we're going to populate inside the function with the values that we compute. The bit down here is less interesting, but all we're doing is going to print the results after we've done that computation. So I'm not going to go over that. It's just some basic printing code. And then if we look up above, I have this function prototype sort of set up for evaluate ODEs. Notice that it's going to return nothing, and that it's going to take these 3 things. First is the state value vector or array. I have a const declaration here because we're not going to manipulate that. We're going to leave it constant inside the function. And then it's going to take in these 2 double precision arrays that we will manipulate inside the function. And our job is to do that manipulation. So we need to fill in right here how to populate the values, given the state values, how to populate the values of the Jacobian and the right-hand side of the ODEs. So we're going to generate some code that's going to go in that bit there. So Aaron showed you the C code function. There's a class that is operating behind the scenes anytime you call those kind of functions, and we call these printer classes. So we have a variety of printer classes, from printing to LaTeX, from printing to the different codes that you saw, pretty printing, etc. But we're going to load in explicitly the C99 code printer here. And all you have to do is initialize it with no arguments, if you don't want to provide any. And then how do you use it? Well, all the printers have a method called doPrint. And if I pass a SymPy object, in our case this matrix, to that doPrint method and print it, it's going to try to print it. Interestingly enough, here it says this is not supported in C, this immutable dense matrix that we have, and it just gives us the sort of SymPy representation of that. So why is that? This next bit here explains that some, or hopefully all. In C, we have to make assignments. Okay, so I I can't just print necessarily the right-hand side, which are just these arbitrary expressions, without assigning them to a variable. It doesn't really mean anything useful unless you assign the results of those expressions to a variable. So I already explained how you sort of instantiate an array, and then you can, I showed you how to populate it, like double-clicking is not a good idea on these, how to populate an array like so, but you can also index into each item of the array and then pass in our case, a double precision value or a computation that would produce one of those. So we need to ensure that SymPy code printing prints this left-hand side of the equal sign in addition to the right-hand side. So we introduced the matrix symbol, and the matrix symbol is how we sort of provide what the left-hand side of all those assignments are going to be. So we're going to create a matrix symbol called RHS result, which is the variable name that I want, of the correct shape, which matches what our right-hand side is going to be. So I can create that matrix symbol, have a look at it. Notice that it indexes into a 2D array by default when you print it. But if I pass in that matrix symbol now to a keyword argument to the doPrint method called assign to, it's going to do the right thing. And notice that I get the first index and I assign that first expression to it. So I have the left-hand and right-hand side of this assignment in the printer. And we can scroll through and see all 14 of those array assignments. So this is a valid C code now that has these expressions assigned to the entries of that array. Okay, so with that new knowledge, print out some valid C code for the Jacobian matrix. You can take about 5 minutes for that. And take down your sticky notes, which I think look like they're all down, and give us your blue one when you're ready, when you're done. Okay, I think that's most everybody. So you can do the same thing that we did above. We basically want to print the Jacobian now, and differently, slightly differently, we want a matrix symbol. I think I've got SYM, matrix symbol, and I called that, I think, Jack result. Maybe I should put this on a separate line so it all fits. And we can pass in the shape. One quick way to do that is you can do that with Python to sort of expand that tuple, and then we'll call that Jack result. So if I create that matrix symbol and then pass in this, and do I have enough parentheses, and then I print, we will get 196, and notice that it takes care of this indexing already. The default is that matrices, 2D matrices, get mapped to 1D arrays in the code generator, and we get all of those values there. So you can print the Jacobian quite easily. Any questions at this point? Okay, let's move on. So what if you want to change the behavior of the printer? It's often useful, maybe you want to change variable names, maybe you want to use a special function that you need, or use a library function, and you want to change how the default printing happens in these printers. All of the code printers have these methods that start with underscore print. Now if I do underscore print underscore and I hit tab, notice that I get all kinds of different things. All of these things are all the different objects in SymPy that you might want to print. So in general, all of the printers have a method defined on them that tells the printer how to print that particular object. Here's some matrices, how to print the infinity symbol, how to print an integer, right? How to print a list, how to print matrix elements, matrix symbols, etc., etc. So if I sort of use those, or look at those, let's just look at matrix symbols since we were using those, and I double question mark, I could look at the source code. And for some reason that
You gotta pull it up.
I printed, oh, it just prints the name. I guess it calls, is it called symbol? Let's look at symbol because should have used the example I already had. Some of these may or may not be. So if I open up print symbol, which is just a basic SymPy symbol, we notice that that method takes the instance of the object and then some kind of expression comes in. In this case, it would be a symbol object that would be coming in. And then inside that function, you basically need to look at that symbol or expression that comes in and do what you want to do and return ultimately a string that gives a representation of the printing. So if I were to return like a LaTeX printer, I might have dollar signs wrapped around whatever my LaTeX expression would be, etc. Question?
Why is it using the super of C89 for the printer and not the super of C99?
In this case, I'm probably going to get this wrong, but the C89 is a subset of C99. So when C99 came along, there's new things that were added to the language. So a lot of times we can just use the C89 printer. So we have a hierarchy of classes that cascade, right? There's a code printer, a C code printer, a code printer that subclasses from a printer, and then a C89 printer that subclasses from the code printer, and a C99 that subclasses from the C89, probably.
This function is actually defined in the C89 class.
Yeah.
And C99 is a subclass of C89.
So they're not, they may not be always as super clear, and maybe I should have picked one that was simpler. But the gist is that inside of that, you get the expression, you do something, you look at that expression, and then you return a string from there. So let's just play with that. I think it'll be easier once we play with it a bit. Say I want to make a custom symbol printer. So here I have my code printer, which is a new class name, and I'm going to subclass the C99 code printer, and I just want to change how the symbol prints. And in this case, I will define a new method, just like we saw, the print symbol method. And then anytime it finds a symbol, it's going to do what I say here. And in this case, I am going to return self._print. No matter what symbol you pass in, I will always print ni. All right, so I just give it a string. I return a string. And another key point here is that I didn't just return a string. I passed it to this defined _print, which is a very general print method that will dispatch whatever you pass it to the correct printer. So if I were to put a symbol in there, it would call print symbol. If I would put a list in there, it would call print list. And in this case, I'm passing a string, and it's going to call print string ultimately. So it's good practice to always call self-print instead of just sending out the string, so that if you have a complex expression, that it will recursively go through and make sure it gets all those pieces. And I don't know if that's probably losing everybody there, but we can talk about it more. But in this case, I'm essentially just returning a string. So I'll define that class, instantiate it, create a symbol, and now if I call the doPrint method on my class, instead of printing the symbol like expected, it just prints this string that I created. So you can manipulate any object in SymPy and cause it to print in a different way. Any question? How about questions right there? My guess is I probably lost people. Everybody got that? Raise your hand if you did not understand that. Nobody's going to admit. All right. Fantastic. So now you get to try printing, subclassing a printer, changing how it prints. In this case, in our ODEs, we have Y0, Y1 through Y13. And we'd rather it say state vals 0 through 13, right? We want to replace those normal symbol prints with the array notation in this case. So there's two solutions here if you want to check, but let's take 10 minutes and try to create a printer that will print all the Y symbols like I have above there. And if you're fast, you can move on to this bonus exercise and try to make another type of printer. All right? So let's take 10 minutes and do that. Okay, I've got a solution here that I tried. I basically said, if you find the symbol that gets passed into print symbol in my state matrix, get its index value, and then print this string, state values, where I replace the curly braces with index. We can see if that works. So I can create my printer. And then print my printer, do print. And in this case, we'll try the right-hand side of ODEs, and we'll also need to assign it to our result. Close the parentheses. And it looks like that works. So now I have all of the symbols that were the Y's replaced with the array, indexed array values there automatically. So now this would more properly work with my function that I showed earlier in the C template. Anybody get the bonus exercise? Few people? So in this case, I'll just briefly say, in this case you had to do a POW object, right? A power, taking something to a exponent, and that particular expression has two attributes, a base and an exponent, and you can replace those. Here was my solution. I basically said if the expression is an integer, if the exponent is an integer and it's between 0 and 4, just do a expanded multiplication, and otherwise return the printer, the power printer from the superclass. Yeah, so I could paste that in and run it, and then it prints as x times x instead of pow x comma 2. So you can have a look at that a little more. Okay, so we've got a little less than 10 minutes. I'll probably have to fly through this last bit. But another useful thing is something called common sub-expression elimination. A lot of compilers will do this for you if you set the proper optimization flags. But the gist is if I have an expression, two expressions like A and B, both of them have x times y in it. And a computer doesn't really need to do x times y twice. We could do x times y once and just replace the result of that in these expressions. So this is called the sub-expression, and it's common to these other expressions. But SymPy can do this pre-compilation for you. And it becomes useful in particular when you're not using optimization settings and with different particular compilers and things, and also find that it increases the compile time. And our CSE is reasonably fast, even for large expressions, and you can save time sort of further down the road. So we have a function called CSE, and oh yeah. And it takes some expressions as its argument, and then it spits out, if you look at the returns, the replacement, which are a list of symbols and expressions, tuples, and then the reduced or simplified expressions. So let's see what that looks like. If I call CSE on the right-hand side of the ODEs, and then I have a little loop that just prints those, we see that it finds all of these sub-expressions in our ODEs. Right? 87 common sub-expressions that it found that were common to those larger expressions. And then it always returns a list of the simplified expressions because you can pass in multiple. So we're going to grab the first one, and then you'll see how our longer multivariate polynomials have been replaced with all these sub-expressions here, all these x's that were defined above. You can also pass in multiple items, so I can get the common sub-expressions that are in both the right-hand sides and the Jacobian. And then we see there's some odd, 200 and some, sorry, my scrolling is not that great, 200 some sub-expressions. And then you can look at the simplified right-hand side and then the Jacobian, which looks a little simpler. All right, so this is particularly useful. So the last exercise, and we've only got 5 minutes for that. Sorry that it didn't quite get through a little faster, but the goal would be is to create a bunch of sub-expressions for both that are common to the right-hand side and the Jacobian, and then output the valid C sub-expression, simplified expressions for the right-hand side result and the Jacobian result. And I've given you some clues here. One is that there's this assignment object that is useful. So if I print an assignment object, I can print a left-hand side and a right-hand side by passing in a symbol and a value in this case. So that's useful. And then here I show you how I can override the immutable dense matrix method. And when it gets our matrix, it calls CSE. And then it sort of builds out the correct printing for us. So that is a printer that can take a single matrix, print valid C code here that we want for all the sub-expressions, and then an array of the other expressions. Okay? So the exercise is then look into how you might be able to use print list so you can pass in two expressions, both the right-hand side and the Jacobian expression, and generate all the sub-expressions and then populate the two arrays in C with the simplified expressions, as I described in the top of that. So you can write your answer there, and 4 minutes. It might be a little hard to get that one done. But you can also look at the solution, and if you're really fast, you can try to compile your C program and see if it actually functions. Okay? So, yeah, should I just go through it since we're out of time? All right. Okay, so let me just copy my solution here. Good idea. So what I did is I overrode, I guess I need to stay in front of the mic. Yeah. I overrode both print list and print immutable dense matrix. So in the immutable dense matrix, I said, well, if that matrix has a certain shape, print it differently. I knew that the Jacobian was a 2D matrix and that the right-hand side result was a column vector. And so I sort of just check here which one it is and make sure that I assign the right variable to them. And then I overrode the print list so I could pass in a list of SymPy matrices. And in this case, I basically just CSC the list of expressions right here, and then collect all the sub-expressions, make my assignments right here. So I assigned the sub-expression, the new variable, to the expression. And then I also print the simplified matrices. And I did a quick hack here to just replace all the y's with state underscore vals also. So you can look at this after the fact, but if I run that, I get a name error, and that is because I haven't defined state array map somewhere. Oh, I think that's in my solution, my second solution to the above problem is where we'll find that. Right. We got a lot of code generated here. So right here, I have these two lines, which I'll bring down. So you can take a look at this in the break to try to get a better idea of what I'm doing. Okay, so I have this map that maps the state vals, and then I print, and I get all of my sub-expressions, and notice that state vals has been replaced. I get all the sub-expressions, and then I have the right-hand side result, the 14 elements of that, and then the 196 elements of the Jacobian result there. So that is quite a few lines of generated code that SymPy helps us do fairly easily. And just for fun here, I'll show you the last bit. I have a little template of the code that I had before, and you can use our new printer to generate a file. So here I take the C template, I use my new printer right there to print out what I want, and I plug it in to the function in this spot right here where we need to fill in the code. And then I write it to a file, a C file. And that's what the C file now looks like, right? We see our prototype, we see all the computations it has to do, and then this is different on every operating system depending on what compiler you have, but I'll run GCC here to compile that new file. Looks like it compiled with no error, and then run it, and it does my calculation. Right hand side, it calculates the values, and the Jacobian evaluates too. Okay? So you'll have to dig through that last bit a little more, probably to see some of the details, but the gist here is that we learned how to subclass printers, and change how they print so that we can do custom things with them. And then we've printed a fully functioning C program now that also use common sub-expression elimination to give us maybe some faster compile times and potentially more efficient computation. Okay? Okay, so let's take a we'll take a 5-minute break. So come back at 6 after, and if you have any questions, come up, and then Kenny's going to lead us on the next round.
So we just saw how to use code printers to generate code that evaluates expressions. So we're going to take that one step further with code generation. And so we'll go ahead and get started. This is the right after the hard way, the harder way. This is the easy hard way, which I'm not sure if that's accurate or not. And everyone else finished on time. I'm not sure that I'm going to be able to finish on time. I'm just going to go through it at a nice pace, and if we don't get to the end, hopefully you can just take a look at the rest of it later. I hope it's written clearly enough that you can work through it on your own. But if you run into issues, you can go to the GitHub page for this tutorial and file an issue. So the point of this tutorial, or this part of the tutorial, is to write a, we're going to see how to write a Python function, just as kind of a demonstration of what Python is if you're not familiar with it. And then we'll use SymPy's CodeGen function to take code printing one step further. Not only does it print the C code that it corresponds to an expression, but it'll actually put it into a function and then put that into a file that you can then compile. And then we're going to wrap that code using Python. So that's one use case for Python, is to wrap existing C code. And then we will use SymPy's auto-wrap function, which can do all of this for us rather than us doing it manually. And then last, if we can get to it, you can actually now pass a custom code printer to auto-wrap and some preprocessor statements to get be able to use a external C library with your auto-wrapped code. So we'll go ahead and get started. These are just a few imports we'll be using throughout. So every SymPy thing is going to be under the SYM namespace. All right. So as a little quick introduction to what Python is a compiler and a programming language. And it is used it's used to generate extension modules for Python. So Python allows you to write C code and compile it into a binary that you can import just like a normal Python module. And so the functions that are declared or defined in that module can be imported and used just like normal Python functions. And so the Python language is sort of a creole of Python and C, but it's primarily Python with some keywords added that allow you to specify data types. So you can see this is very Python looking, but it has these keywords like int, cdef, float that tell it what the type of these things is. And what this does is it basically it takes the dynamicism of Python away. And so it knows now that this is an integer and this is a float. And so it doesn't have to look up the types of every object before it can do things like add and multiply and everything. So the compiler is going to take this Python source code and turn it into C code. And it's kind of a specific flavor of C code that includes python.h, so it uses Py objects and things. And this is what allows it to be compiled into a Python extension module. And then, so aside from writing Python for computations, like this function up here, you can use Python to wrap existing C code, and that's primarily what we'll be focusing on for this part of the tutorial. But just as a quick example of the Python language and what it can do, I'll go through a little demonstration of generating Fibonacci sequence numbers. So if you're not familiar with what the Fibonacci sequence is, it's just a sequence that's initialized with 0 and 1 as the first two elements, and then every element after that is defined recursively as the sum of the previous two elements, okay? And so our objective is to write a function that computes the nth Fibonacci number. And so this is a simple, pretty simple function. It's just an iterative solution. And so it generates numbers. And if you run that and then run the next cell, you can see that it generates a list of the numbers, so 0, 1, 1, 2, 3, 5, etc. So we can see how long it took or how long it takes to generate the 100th Fibonacci sequence number. And it takes about 4.9 microseconds on this machine. So now let's go ahead and implement the exact same thing with Python. And so since Python is basically Python with types, it can be a little more complicated than that, but in some cases it's pretty simple. We can pretty much literally copy and paste the code and then add in types and see what it does. So there are a few, anyway, that's the benefit, is that it's so easy to do that, but it comes at the cost of having to compile the code before you can run it and import it. So there are a few ways to go about the compilation process. I'll use a couple different ones in this part of the tutorial. So the first one, since we're just writing Python code, there's no really complicated stuff going on. You can use this Python magic command in Jupyter Notebooks. And to do that, you can load the Python extension. And this will take the contents of the cell, compile it into the C code, the kind of extension module flavor of C, and then compile it, and then import its contents into your namespace so you can use it just like a normal Python cell. So go ahead and run this, and you can see that it's really just exactly the same thing, but with cdef float, or cdef double, A, double B, declaring the types of all of these things. You can still use for I in range n, that kind of stuff. And so if you run this, it should compile, and then you can time how long it takes to do that, and you can see 217 nanoseconds. So it's several orders of magnitude faster than the pure Python implementation. And all we had to do was add these types and then use a magic command to compile it. Does anyone have any issues with getting it to run? It should be pretty easily cross-platform, but yeah, okay, good. It gets more complicated, so we'll see how it goes as we go. So if you want to know a little bit more about writing Python for computation, there's an extra notebook I was going to have in this, but I just kind of cut it out because it was just extra material. So there's, that's contained in the notebooks folder of the repository. And even better, there's a tutorial going on right now on Python, and it goes way more in depth into writing Python code. And this is just a link to the GitHub page for that tutorial. So you can check that out later if you're interested. Okay, so we're going to switch gears a little bit and go back to the main point, which is we want to generate C code, and then we want to be able to compile it and then call it from Python. The reason we want to be able to call it from Python is we're going to use SciPy's ODE int to integrate the equations and plot the results and everything. So SymPy's code gen function is what's going to take the code printing and then wrap that into a C function and a C file and write them to the file system so we can use them and compile them into an extension module. So just as a really quick overview or review of the system we're looking at, this is the water radiolysis system that Jason talked about. So it's a system of ordinary differential equations. We have these 14 state variables, y0 through y13. That's the left-hand side, and on the right-hand side we have these functions of all the state variables and possibly time, although none of these functions actually have time in them, but in general, ODEs can. So we're going to represent these state variables in a state vector that's a matrix, a 14 by 1 matrix, and the right-hand side is going to be a 14 by 1 matrix of these expressions that we call RHS of ODEs, right-hand side of ODEs. So we can start by importing the ODEs. This is exactly the same stuff that Jason showed earlier. And we just print the first row of the right-hand side matrix just to refresh on what it looks like. So it's these polynomial expressions in the state variables. So now we can use SymPy's CodeGen function, which is under the SymPy utilities CodeGen namespace, to output C source and header files that compute the right-hand side of the ODEs numerically, given the current value of all the state variables. So we'll import that, and I'll just go ahead and uncomment this so you can see the doc string. So yeah, you can see it takes what's called a named expression. This is just a tuple or a list of tuples giving a name and an expression for each thing you want to evaluate. It can take multiple expressions, but we're just going to use one. It takes a language. You can pass some other stuff to it. I don't think we use much else right now. So we just have the one expression we're interested in computing. That's the right-hand side of the ODEs. It's actually a matrix of expressions, but that's equivalent to just being one expression or one kind of SymPy object, I guess. And what we want CodeGen to do is generate a C function that takes the current values of the state variables and computes the derivatives. And so I guess zooming in means you can't really see everything, but so you have what CodeGen will return, a list of tuples. It's the C file name, the C source code as a string, the header file name, and the header source as a string. Okay, so if you run that, we can go ahead and print the C source code, and I'm going to zoom out a bit. That's okay. All right, so the comments get a little messed up, but so it prints this little banner comment up at the top. It prints out the include statements that you're going to need. So it includes the header file that it generated and math.h, so it can make use of pow and sign and things like that. And then it generates this function. And the formatting is a little bit hard to tell what's going on, but this is the function signature right here. So it's void, it doesn't return anything. It's called CODEs because that's the name that we gave right here. And then it takes the state variables, y0 through y13, and it takes in the output as a pointer. So a lot of you said that you knew C. So those of you who know C, this is not a super complicated use of pointers, but those of you that don't, the only thing I'm going to mention is that in C, it's idiomatic to pass in, to pre-allocate some memory as an array, and then pass in the location of that memory and the number of elements it holds, instead of passing the array itself. And so when you do that, it just takes the memory location, fills in the values because it knows the type of thing that it's holding, and then you don't actually return anything. The memory is now modified, and so the output of the function, it doesn't need to be returned. So that's all you need to know about pointers for right now. And so you can see that it generated all the code. There's a couple of things to note here, though. It takes in each of the state variables independently or individually, which isn't ideal. And it also takes in the state variables in the wrong order. So when we called the CodeGen function, we didn't tell it that we have this matrix of state variables and what order they're in. It just took the right-hand side of the ODEs, and so it alphabetized the state variables. In that case, Y1, Y10 rather than Y2 comes next. So that's not ideal. It also gave us this kind of automatically generated name for the output, and so we'll deal with that too. So starting with just the taking in the state variables individually, and this will actually end up taking care of the ordering problem as well, we can use this matrix symbol thing we saw before, so we can instead of using the states matrix of individual symbols, now we have a matrix symbol where we can index into it the individual elements. So what we need to do then is make use of this matrix symbol inside of our ODE's expressions. And Jason kind of glossed over, I don't think he actually showed this, how to do this in the previous notebook. He did it by subclassing the printer. There's another way to do it. All we want to do is take a map of these symbols, Y0, Y1, etc., and map those to these things right here, Y00, Y10, etc. So this is the, this corresponds to the symbols that are in our states variable. This corresponds to the 0th element of our Y matrix symbol. And so we want to map those. And so you can create this state array map. And it does this. So it's just a dictionary that maps Y0 to Y00. And then we need to replace the occurrence of Y0 in our right-hand side expressions with these. So you can use this extra place function, and it takes a map just like what we just generated. And so what you can see is when we run that, our the first row of our ODE matrix, it has now Y00 squared instead of Y0 squared. So the pretty printing actually kind of gets rid of what's actually happening. But now this is an indexed variable, a matrix symbol that takes an index rather than a symbol Y0. So you can now use this RHS of ODEs instead of RHS of ODEs to generate code, and you can see what happens. So you can just take this little template and figure out what arguments it needs to take in order to generate the code. And you can look up at the above example to see an idea. and yet another solution. I just put some white space above the solution, so if you don't want to cheat, you can avoid scrolling down. So go ahead and take a couple minutes to see if you can generate the code and print it out and see what it looks like. Those people got to figure it out. So if you didn't, you can just scroll down and see the solution. We just pass in this RHS of ODEs end instead of RHS of ODEs, and then see what it prints out. So now the signature of our function is much shorter and quite a bit cleaner. Instead of having individual state variables, we have this pointer to pointer to double, which is representing an array of our state variables, and that's what we want. We're going to pass in an array of our state variables rather than the individual ones, which will be nicer when we talk about ODE int later. So it still has this issue of kind of this ugly variable name. We can actually change this, and I'll show you how to do that. So so you can make another matrix symbol, dy, and this is going to represent the left-hand side of our equations. And so it's basically the same thing. We just generate a matrix symbol that's the same shape as y. And what we're going to do now is we're going to form an equality object that equates the left-hand side, this dy, with the right-hand side. And you can use the indexed version of the right-hand side of the ODEs. You form an equation, and then you can use that equation rather than just the right-hand side expressions and generate code and see what comes out of that. So take a couple minutes to see what happens there. Okay. It looks like most people are getting there. So in this case, you form the equality. You just put the left-hand side, and then the right-hand side is the second argument of the EQ function. And then just pass this ODE EQ instead of the right-hand side, and it will print out. In this case, we're just going to print the header. I think I forgot to mention that, but this will just print out just the header source, so you can just see the signature rather than all the generated code. And now we get a nice clean function signature. It's called CODEs. It takes a pointer, which represents an array of our state variables, and it takes a pointer to an array that represents the values we want to fill in, which represent the derivatives of our state variables. So I kind of already explained some of that. Okay, so now just so we can actually compile this code and use it later on in the tutorial, I'm actually going to use the two files keyword argument of CodeGen and just run the exact same thing. In this case, it doesn't return the source code as a string, it just writes it to the file system. So you just write that, and you should be able to see in your, if you navigate to the notebooks folder, you should be able to see the CODEs, C and H files. Okay. So now that we've got some actual source code written to the file system, the question is how do we get this into a Python extension module so we can call it from ODE int. So now we're going to work on wrapping generated code with Python. You basically write a script, a Python script that does two things. It just reiterates the function signature that's found in the C source code, and then it implements a Python interface to that C function. And so we'll see an example of wrapping this CODEs function in order to be able to call it from Python. The build system of Python is able to take the wrapper source code and the C library source code, compile and link them, and then generate an extension module that has functions in it that you can call. This process is a little different depending on how exactly you want to use things. In this case, we're going to use this Python PYX import to do everything for us. And in that case, it's going to write the contents of the cell to a file that has the name that we specify with the PYX extension that indicates that it's Python source code. It looks for a mod name, just the name of the thing we generated, .pyxbld, the Pyrex build file, for instructions on how to build everything. So if we don't tell it like where the C files are that we want to link with our extension module, it won't know how to find them. So we just basically need to tell it where that is. And then it will build everything into extension module, and then it's going to import everything that we declare into our namespace so we can just call it like normal Python functions. So it does a lot of stuff in the background, but it does need to be coached on how to actually do the compilation process. But this file that we're going to have to write is pretty similar to what you would put into a setup.py file. If you're going to write Python code that wraps C code, you would do a similar thing there, and I'll kind of show you how that works. So in the end, this Python Pyrex import works similarly to the Python magic, but everything's a little more complicated now because we need to tell it where the C library is. So in either case, we need to tell setup tools / Python the name of the extension module we want to make, the location of the Python and the C source code, and the location of the headers needed during compilation. And so this will include the header of the generated code that we made and NumPy's headers. We're going to use NumPy within our Python source, and that's one of the cool things about Python actually is it uses NumPy fairly well. And so we'll tell it where NumPy's headers are so we can use NumPy's C API. And so we're going to call our extension module SciODEs. And so here we'll write our build file to tell it how to build everything. So I'll just break this down. It's not super complicated, and again, it looks a lot like what you would put into a setup.py file if you're packaging this stuff and you want to ship it to someone. So you can import setup tools.extension. There's an extension class. That means extension module. That's what we want to make. So we're going to tell it the module name. We're going to tell it the sources, and so the sources are just going to be the Python source that we have, and then the CODEs file that we had. So this is just telling it what are the things we need to actually build to get this extension module to work. And then the include directories are going to be the current directory, because that's where we wrote the codes.h file, and then NumPy's headers you can get with this get include function. Okay, so when you run this cell, it will write the contents. It's got this write file magic that will just write the contents to a file that's called sciodes.pyrex build. And so you can look at that in the directory if you want. So finally, we can write our wrapper code. And the first thing we do is specify we just replicate the function signature from the header. So this is literally just copied and pasted from the header file we generated. And this just says that this is where this function is located. And then here's our wrapper. And this is just our Python interface to the C function. And this is, by the way, this is all Python source code, basically, right? So it's going to write this file, sciodes.pyx, and then the sciodes.pyx BLD file will tell it how to build everything. So the wrapper, we're going to make this wrapper conform to the ODE int interface. And if you remember from, I think Björn talked about it, it takes the array of the state variables at the current time and a scalar time. And so this syntax looks a little ugly, but I'll break it down. So we get the y is going to be a NumPy array. Its type is double. So that matches with the C code. It takes an array double. And then it's a one-dimensional array, and it's called y. And then it takes a double t. Okay, and then like I said, the pointer thing is you just pre-allocate memory, and then you pass the C function where that memory is located rather than passing in the thing itself. And so we pre-allocate our dy. This is going to hold our result, and it's the same shape and everything as y. So we can declare it as an empty array of the same size as y, and also you can give it the d type. So now the final thing is we call the C function, and then we return its result. So we call CODEs. This is a little bit, this might be a little confusing, but basically we grab a pointer to our array by getting the data attribute. So NumPy arrays all have the data attribute. That is basically a pointer to the raw memory of the array rather than all the array itself. And then we just cast it. This is how you cast in Python. Cast it to a double pointer rather than, by default, this is a pointer to character, a char. So we do that for both of these. And it's not super important exactly what's going on here. If you are not familiar with C, you can treat this as a recipe, and it should work. So if we run that, this should hopefully build in the background and give you a SciODEs function that you can now call. So your next exercise is just to use NumPy's random.randn, generate some random numbers that you can put into your SciODEs function and see what if it returns something reasonable. Let's go ahead and try that. Okay. I think we'll try to move on. This is towards the end of this section, and we'll start a new thing, so this won't cascade to problems later. If you run it, you should now have this SciODEs function. So you can generate some random vowels. The shape of this should just be 14 by nothing. So it's a one-dimensional array of size 14. And then you can call the SciODEs function with the random values. And then you need to add in the time value. You can use any time value because the equations don't actually make use of it. If you run that, you should get some numbers. Yours will probably be different than mine. So now, our goal was basically to now be able to use this Pythonized function within ODEInt. So now we have this function that takes the interface that ODEInt expects, and so we can use it like we've already seen how to use ODEInt, so we'll just go ahead and run it. I've added a couple of just utility functions in our package that comes with the tutorial. There's a function that just generates some initial conditions that are reasonable for this system, and then just plots it in a kind of reasonable way. So we can make some initial conditions, and then just run ODEInt, calling the SciODEs function, give it the initial values and the time values we want, and then plot it. And we should get something like that. Okay? So just to kind of recap what just happened, we took a symbolic expression, which is a matrix of ODEs. We use the Cogen function to generate C code that evaluates the right-hand side of those ODEs. We played around a little bit with matrix symbols and stuff like that just to get the kind of function signature to look nice. But otherwise, it's just running Cogen to generate C code, and then we wrote a Python wrapper around that C code. And so everything that we just did is sort of just a recipe. You can use that for lots of different problems that you might want to use it for with ODEInt or really anything, any kind of numerical solver or whatever. The Python wrapper won't change too much, but yeah, question.
So if I understood it correctly, once you've done this process, you have the output of it. You could use it on another system that maybe doesn't have SymPy or whatever, because it's all already happened and created the Python output, or would you still need SymPy?
You would have to redo it for whatever system you want because it took the symbolic expressions and generated C code. It's like hard-coded C code that evaluates that specific system. So you'd rerun that. The Python wrapper could basically be reused, but you'd have to recompile with the new C code that you generate. Yeah, is that it? Answer the question. Any other questions about what we just did? Okay, cool. So now we'll see how to avoid doing all of that and use AutoWrap. So AutoWrap, as the name implies, automatically generates a Python wrapper for us. And there are some advantages and some disadvantages to this. But this is basically another kind of layer of abstraction on top of everything. So we started out with just taking a SymPy expression, generating a little snippet of code using the code printers. We added on top of that the code gen stuff, which takes that little snippet, puts it into a function in a file. And now we're going to add a little layer on top of that that takes the file, writes a Python wrapper, compiles it all, and gives you back a function that you can call. Okay, so we can import AutoWrap. It's under SymPy utilities.AutoWrap. And you can look at the doc string here. Its interface is sort of similar to CodeGen, but slightly different. In this case, it just takes the one expression. It also has this extra backend keyword. Okay, and in this case, by default, it uses F2Py, so it's, we're gonna actually use the Python backend instead. So we'll have to specify that. The language argument is similar, but it can actually be inferred if we're using the Python backend, where it's implied that we're gonna be using C code as the language. So we won't actually be using the language keyword argument. It takes a few other arguments that we will hopefully get to see toward the end. But anyway, we can use AutoWrap, and what AutoWrap's going to do is going to take, like I said, it's going to take the expressions, generate C code, generate a Python wrapper around that C code, compile it all into a Python extension module, and then give us back a function, a binary function that is just a Python callable. We can call it with arguments, and it comes back with results. So it's pretty cool. It does everything we just did for us. And so you can call it like this. We're going to give it the ODE EQ so that the function interface is the same as the one we just used with CodeGen. Give it the backend with Python. And then it also takes a temporary directory. And I'm just going to put everything in this AutoWrap temp. I'm actually going to, I think I have some leftover stuff, so I'm just going to get rid of my old ones. There, okay. So if we run that cell, what is it doing? Okay, run that cell. It will do everything in the background for us. You can go, actually this is an exercise. So now you can use this notebook tab, the main notebooks tab, go into the directory we just created, which is called AutoWrap temp, and look at some of the files that are in there and see if you can kind of map the files that it generated to what we just did with CodeGen manually. So just take a couple minutes and kind of look through what it did. You might also be interested in seeing how it did the Python compilation stuff. It's slightly different than how we did it with the Pyrex build file. So you can take a look at that too. Right, we got about 10 minutes, so I'm gonna run through a couple of the extra things rather than making them like full exercises, so we can get to the last part, which is pretty neat too. So if you go into the notebook cell, you can see this AutoWrap temp directory, and it created a bunch of files. So the first one we can look at is the wrapper module. This is the Python wrapper that we wrote manually. It's a bit different than the one we wrote. One thing you'll notice is that it creates two-dimensional arrays. This is because we're passing in matrix symbols, that is a 14 by 1 matrix symbol y and a 14 by 1 matrix symbol dy, right? So that'll be sort of an issue when we want to use ODE int, because it expects to be able to pass in a one-dimensional array of state variables, and it expects to get back a one-dimensional array of derivatives. So we'll have to deal with that. It also generated the wrapped code. This looks basically identical to the CodeGen generated code, except it uses an automatic name rather than the one we gave it when we used CodeGen. It also generated the header file, and then it has this, I guess I don't really need to look at this, but this is the Pythonized code. This is what Python generates when it takes the Python source code and generates this, the extension module code. You can take a look at it if you want. It's quite, there's quite a lot of code there. And then the setup.py file, I mentioned this earlier. It uses this setup tools extension, or alternatively distutils extension class, to generate an extension module and tell Python or the build tools where to find the source code that it generated and the Python source code. And it also uses the NumPy include, or the NumPy header files. So it works pretty similarly to the manual like Pyrex build file that we generated or we created. But this would be useful if you're actually going to package your Python or your wrapped Python code into a module that you can install with Python, setup.py, install, and things like that. Okay. So I just explained a bit of that here. The next thing I'll do is, I kind of already pointed this out, but we can't pass in a one-dimensional array of state variables, so in this case I had to make the shape 14 by 1 so we can get outputs, and then the output is a two-dimensional array. So that's not ideal for using with ODE_int. So our solution for that is going to be to just write a little Python wrapper around our auto-wrapped C code. And all it's going to do is just take in the one-dimensional array of state variables, add an extra dimension so we can pass it into our auto ODEs function, and then squeeze the result so that it's one-dimensional again when it comes out. So you can run that, and then we can now put in a one-dimensional vector and get out a one-dimensional vector. Also notice our wrapper, we included this time value or time variable in the signature because auto-wrap didn't add that. We could actually add that with auto-wrap. I didn't show that, but you can actually specify additional arguments if you want to. It's just a keyword argument to the autogen function. And then finally, we can use auto-wrap to generate a function that evaluates the Jacobian like we have been doing. And I'll kind of skip this also. Got about 5-7 minutes. So all we're going to do is compute the Jacobian analytically, call auto-wrap with the Jacobian as our expression. Everything else is the same. And then write a wrapper around it again because it's going to take in, it expects a two-dimensional array input, so we're just going to add an extra dimension to that. The Jacobian is actually a two-dimensional entity, so you don't need to change the output at all. And then we can just call it with some random values and make sure that the shape is correct. And it should be 14 by 14. Okay. And finally, we can use our auto ODEs wrapper, the function we made to wrap the auto-wrapped ODE evaluator, and the Jacobian as the defun, and then generate our plot. This should look similar to what we had before. Okay, any questions about this before I kind of just get to the last part and touch on another cool thing about auto-wrap? No? Okay. So the last thing we can do is, this is actually a very recent feature of SymPy. Auto-wrap accepts a custom code gen object. And a code gen object is one layer on top of the code printer. So the code gen object is responsible for taking the code printer that generates like the snippets of expression evaluation code and wrapping it into a function and a file. And so the code gen object actually takes a custom printer. And we already saw we can implement some custom printing by subclassing subclassing a printer and overriding some of its methods to do something. And so we're going to use this to actually use a external library. So say we have some library, in this case, I'm going to look at the fastapprox library. This is just a headers library. You can go on GitHub and download it. It's already downloaded into the package that we provided. But it's just some header files that basically approximate things like power and exponentials. I think it's got sinusoids too, logarithms. And it just does that with limited precision with respect to like math.h. And so I forgot to evaluate this. So this library provides a fastPal function. And so the point of this is just to see how we can take an external library and use its functions in place of what auto-wrap does by default. So auto-wrap, if you noticed in the generated code, any of these should be fine, wrapped code. You see that it, that's for the Jacobian, let me look at the other one. Wrapped code 0. You see that it has this PAL. We're going to replace that with fastPal, okay? And so in order to do that, we're going to have to replace how the printer generates this string PAL of the base to the exponent. And we're also going to have to include the header file that specifies where the fastPal function. So we can guess we can try to do this as an exercise. It's the last thing. So you can take the last few minutes and try to generate a custom printer that will use fastPow instead of POW, and then instantiate it, and then try to print out x cubed and see if it uses fastPow and see if it works, basically. And then after that, if you get it to work or you don't, we can run it and see how it generates the code. So go ahead and spend the last couple minutes trying to do that. Okay, never mind. We'll just go ahead and run it. Just so you can see how it works. So it's not too bad. All you do is the expression that gets passed into the POW function has a base and an exp attribute. And then we can replace, instead of POW, we're just going to return fastPow with these two things. Instantiate the custom printer, generate an expression x cubed, and you can see it just prints out as fastPow x3 instead of POW x3. Okay, and so now we're going to create a code gen. This corresponds basically directly to the code printer, C99 code gen. We'll take a code printer and wrap what it generates into a function. And then the last thing is we need to add the preprocessor statement that says we need to include fastPow.h. If you're not super familiar with C, this is just equivalent to like include math.h to give the POW function. Now we're going to use fastPow instead of POW. And so we append the preprocessor statement to our CodeGen object. And then the last thing I promise is specifying where this fastapprox library is. And so we've put this into a subfolder of our SciPy 2017 CodeGen package. So we can find that by just looking for the CodeGen vendor init and then looking for the fastapprox directory under that. So you can run that. And finally, use ODE EQ. This is the equation that has our dy is equal to our right-hand side of the ODEs. We pass in our custom CodeGen, and then we just need to tell it that there's an additional include directory, and that should run, I hope. And now you can look at the code that it generated. It should have fastPow instead of POW. And now you can run it. It turns out that the limited precision of the fastPow function makes our integration blow up. So you can check that out if you want. You can see that if we use our fastPow implementation, the normal math.h POW, you can see that there's, it's pretty different actually. So when you just evaluate it with some random values, you get like pretty big differences between the outputs. So that's why it blew up. But anyway, the point was you can use an external library, subclass your printer, and pass that into auto-wrap, so you can use external libraries in auto-wrapped code, and it should all just work, in quotes. All right, I think that's it for me. So we can conclude, I guess. If you want to write some feedback, good feedback on the blue, negative feedback on the red, and just pass them up to the top, we'd appreciate that. And I don't know if we had anything else to say.
Yes, thanks everybody for coming. We appreciate the good audience and hope you all have something to take away today. So come talk to us at the conference too. We'd love to hear what you're doing.
There's also